Press plate metallurgy, the microstructural matrix.
When an industrial heavy press closes to manufacture a laminate board, it exerts thousands of tons of downward force. Positioned directly inside this machine is the press plate, a highly engineered sheet of solid metal. This single precision tool dictates the final surface texture, gloss, and overall structural quality of high-pressure laminates and medium-density fiberboards. To function, the plate has to endure 3 concurrent physical stressors: severe mechanical compression, rapid thermal cycling, and constant exposure to caustic chemical resins like melamine and phenol. Precision manufacturers like Moldart engineer tooling specifically designed to operate inside these extreme parameters. Because these stressors attack the tool simultaneously, selecting the correct steel for a press plate is a complex, multivariable optimization problem. A common misconception across the industry is that standard austenitic stainless steel, like grade 304, has enough baseline durability for any pressing operation. Under the specific, repetitive loads of high-pressure lamination, that assumption fails. To build a tool that survives, engineers evaluate 3 distinct microstructural classes of steel: martensitic, ferricitic, and austenitic. Each class possesses a unique atomic structure optimized to perform a specific job: resist mechanical wear, manage thermodynamics, or repel corrosive chemicals. We can map the correct microstructure to the operational load by building a data-driven decision matrix. Selecting the wrong steel grade for the primary stressor guarantees rapid tool degradation and immediate production bottlenecks. We begin by examining the production of high-pressure and low-pressure laminates. The primary mechanical threat in these operations is a structural failure known as telegraphing. Telegraphing occurs when hard, microscopic imperfections in the underlying substrate are forced upward under extreme load, permanently denting or scratching the pressing tool. This chart graphs austenitic 304's baseline hardness. At 18 to 20 Rockwell C, it lacks rigidity to repel microscopic impacts. Martensitic grades like AISI 410 and 420 offer a solution. After heat treatment, their hardness scales up to 40 HRC. By effectively doubling the Rockwell rating, the plate gains the necessary wear resistance to block substrate telegraphing over thousands of cycles. This elevated hardness is also required to protect deep, intricate surface textures, such as simulated wood grain or stone indentations, from collapsing under pressure. For decorative laminate production, standard austenitic steel is a liability. High wear resistance makes martensitic grades a strict mechanical mandate. When production shifts to medium-density fiberboard, or MDF, the operational focus moves away from mechanical wear. In MDF manufacturing, the primary bottleneck is thermodynamic, the speed at which heat can travel through the metal to cure the internal resins. This display compares the thermal conductivity of standard austenitic 304 against ferritic AISI 430. The 304 plate transfers heat at approximately 16.2 watts per meter Kelvin, while the ferritic plate accelerates that transfer to between 25 and 26. That higher conductivity allows for faster heat transfer, which directly shortens the required cycle time for every board. High heat introduces a secondary threat. Rapid temperature shifts cause massive steel plates to physically expand and deform. The severity of this warping risk is dictated by a specific metric, the coefficient of thermal expansion. This vector graph maps the expansion gap. Standard 304 expands at a high rate, roughly 20 times 10 to the negative 6th per degree Celsius. Ferritic 430 maintains a low, stable curve at 11. Because of its lower expansion coefficient, the ferritic plate actively resists bowing when subjected to rapid heating. For MDF boards, where heat transfer and dimensional stability dictate production limits, ferritic 430 is the optimal thermodynamic choice. Beyond internal physics, the exact look of the laminate, from high gloss to matte suede, is determined by the physical surface of the plate. Translating complex designs into metal requires rigorous chemical and electrolytic etching processes. Martensitic structures, like 410, have a crystalline makeup that readily accepts these precise, intricate etched patterns. Regardless of the baseline steel, many of these plates are then finished with hard chrome plating to armor the textured surface against abrasive wear. The final operational extreme occurs when specialized chemical laminates are processed in highly corrosive, high humidity, or severely chloride-rich environments. In these highly corrosive scenarios, neither 410 nor 430 grades will survive without severe pitting. To operate here, engineers must utilize austenitic AISI 316, an alloy formulated specifically for superior chloride and chemical resistance. When chemical degradation is the primary operational threat, engineers sacrifice mechanical hardness and specify austenitic 316 for its survivability. This completed decision matrix provides the operational framework for press plate selection. High mechanical wear dictates martensitic grades, thermodynamic speed dictates ferritic, and highly corrosive environments require specialized austenitic. However, there is one universal manufacturing constraint that supersedes the chemical composition of the steel: dimensional tolerance. For a press plate to apply pressure evenly across a massive laminate board, it has to maintain extreme parallelism and flatness. This schematic shows the threshold required by the modern board industry. Physical variations across the entire surface must remain below 0.10 millimeters. Achieving a microscopic tolerance on a plate this large requires specialized treatments like stretch leveling and pre-stressing, where massive industrial clamps physically pull the steel perfectly flat. These mechanical leveling processes ensure that the plate remains perfectly rigid, even when subjected to the operational loads of the press. High-performance laminate manufacturing requires exacting specifications, governed entirely by applied thermodynamics, strict tolerances, and precise microstructural engineering.